let's start talking about the meaning of these induced fields and how it all comes together. So Faraday's law says there's an induced potential and current whenever we change a magnetic field or a magnetic flux. So let's write that down in terms of what we've been writing so far. Delta phi m, if you get the change in flux, you induce a magnetic field, B. If you get an induced magnetic field, you get an induced current. If you get an induced current, you get an induced potential, epsilon. Okay, so to go back to an example we've done a few times, what if we had a loop in this magnetic field, and let's say that the magnetic field into the page increased. So that would induce a magnetic field out of the page. So there's B. An induced magnetic field out of the page would induce a current around the loop coming this way. So our induced current would be counterclockwise, and that would induce a potential. But what makes the current? That's a good question. So charges only move if there is an electric force, and there's only an electric force if there's an electric field. So the conclusion is that there must be an electric field induced by the change in magnetic flux. So what makes current and potential? Well, it must be an induced electric field. So we know that our induced EMF, our induced potential, is minus change in magnetic flux over change in time. We also know that potential is the integral of E dot ds. So it's electric field over space. So this tells us that the integral of E dot ds is equal to minus change in flux over change in time. So there's a relationship between field and flux. So now let's just think about this in context a little bit more. If I hold an apple up in the air and I let it go, it's going to fall down. If I take the apple away, gravity is still there. The same is true for electric field. If I put my loop in the picture, I'm going to get an electric field induced by the changing flux, and a current will flow. But that electric field is still there even if I don't have a loop in the picture. So even if I didn't have the loop, changing the magnetic field would still induce an electric field. The direction of that electric field would be the direction of motion of the current. So something like this, tangent in all those places. So there's the induced electric field, and that exists even without the loop. So what's the nature of the field? In earlier chapters, we talked about electric field made by charges. We don't have a charge now, an external charge, but there is an electric field, and it's made by a changing magnetic field. Those fields are differentiated as Coulomb fields or non-Coulomb fields. So an external charge makes a Coulomb field, a changing magnetic field makes a non-Coulomb field. Now, Maxwell got in on this around 1855. He proposed that changing an electric field creates an induced magnetic field. And he said that based on symmetry arguments because he saw the link between electric fields and magnetic fields. That led Maxwell to one of his four equations. So it said that the integral of B dot ds equals mu naught I. So we already dealt with that part, but then we had to add on a new part. Mu naught epsilon naught d phi electric dt. So our first term is how magnetic fields act in space. And then our d phi dt term is how fields act in time. And this all together is a wave equation. So the change in magnetic field is a spatial change in magnetic field is linked to a time change in electric field. From this, Maxwell concluded that light was a self-sustaining electromagnetic wave. And self-sustaining means that the change in electric field makes a change in magnetic field, which makes a change in electric field, which makes a change in magnetic field, and so on. So he said that this was a self-sustained electromagnetic wave with a speed of c, which is equal to the square root of 1 over mu naught epsilon naught. So let's just put that conclusion in here. So light was an EM wave with speed equals 1 over root mu naught epsilon naught. That's kind of a revolutionary idea, and it was proved correct by Hertz in 1888, who generated radio waves and found that their speed was equal to this value c. We often say that electric fields and magnetic fields are really the same kind of thing. We use the term electromagnetism, they're tied together. So next, let's just have a quick look at how that's true. First, we're going to have to remember a little bit about relative motion, relative velocity, and reference frames. If I'm in my car and I've got a cup of coffee in my car and I'm driving along, is the coffee cup moving? Well, the answer to that question would depend on who you ask. I'm in the car and I'm driving along. I think the coffee cup looks like it's staying still. But to someone outside watching me drive by, they would say that the cup of coffee is moving. So that sort of relative velocity matters. So in our setup here, let's say that we have Alec. So here's Alec. And let's say that Alec holds up a pair of giant magnets. He makes a magnetic field. And then we have Brittany. Brittany is holding a charge in her hand, and she's running through that magnetic field with a velocity v, and she's holding a charge q in her hand. So a good question to ask here is who sees what? What does it look like to each of them? So what does Alex see? What Alex sees is a charge q moving in a magnetic field with a velocity v. Well, to Alec, he's for sure going to observe that there's a magnetic force on that charge equals QV cross B. And that's the sort of thing we've been talking about. But what does it look like from Brittany's point of view? According to Brittany, the charge is in her hand. Q is still with respect to Brittany. If the charge is still with respect to Brittany, the magnetic force that Brittany sees is 0. Okay, this is kind of a problem. Is there a force on that charge or is there not? Does it accelerate or not? Well, these are inertial reference frames. The two people, Alec and Brittany, they should be able to agree on force, but they don't agree. Well, we said when we started our section on magnetic fields that magnetic fields depend on velocity, but we never said velocity with respect to what. That part is really important. Let's go back and let's look at relative velocity in a first year sort of approach. So let's say that A, our reference frame drawn in blue, that refers to Alec. So A equals Alec. He's like the ground. And then in red we've got Brittany. So B stands for Brittany. She's moving with a constant velocity. And she's got a velocity of Brittany relative to Alec. So that's her velocity. Okay, next we have our charge. Let's call our charge C. So C stands for where our charge is. The velocity of C could be measured relative to Alec or relative to Brittany. Both are valid things to do. Okay, so there's our setup. Now we'll go to our relative velocity equation. And our relative velocity equation says that the velocity of our charge relative to Alec is equal to the velocity of our charge relative to Brittany plus the velocity of Brittany relative to Alec. So that's how we would do a first year analysis of this. So C to A is charge to Alec. C to B is charge to Brittany. And B to A is Brittany to Alec. Okay, so remember this is a vector equation, it's velocity, the direction matters. What if our charge accelerates? If we wanted to get an equation for the relative acceleration, we could just take the derivative of the velocity. So the derivative of the velocity of charge to Alec with respect to time is going to be the derivative of charge to Brittany with respect to time plus the derivative of Brittany to Alec with respect to time. Now remember, we said Brittany was running with constant velocity because these are inertial reference frames. So Brittany to Alex, the time derivative is 0 because it's an inertial reference frame, constant velocity. Well, that leaves us with the acceleration of the charge relative to Alec equals the acceleration of the charge relative to Brittany. So no matter who measures it, they have the exact same acceleration. So both measured the same acceleration. And if we remember that force is mass times acceleration, they must agree on the force on the charge. So if they measure the same acceleration, they have to say that the force is the same. But on our previous slide, we said that Alex saw a magnetic force, but Brittany didn't. How do we reconcile that? So now let's look at things from Alex's point of view, and what does he see? So what Alec made the field. Remember, he was holding up the giant magnets. So he made the magnetic field B, and he sees that the charge Q is moving with a speed, and sees charge Q moving, and charge Q has the same speed as Brittany, same velocity as Brittany, with velocity Brittany relative to Alex. So he sees a charge moving in a magnetic field with a velocity, so Alec observes that the magnetic force is equal to QV cross B, where Q moves with velocity V in field V. And that's the standard stuff we've been talking about. The direction of that force is going to be straight up. So this is the force, the magnetic force that Alec sees. Okay, so that's step one. We've established that Alec, who has made a magnetic field, sees this charge feeling a magnetic force because of the motion in the charge. Now let's look from Brittany's point of view. And remember, we said they had to agree on force. Now let's look at things from Brittany's point of view. So remember, from Brittany's point of view, the charge is still. But Brittany does agree that there is a force on the charge, but she just doesn't think it's a magnetic force because to her, the charge is not moving in an electric field. So if the charge feels an upward force, what kind of force is that? So Brittany and Alec see the same force, which points up. But to Brittany, the charge is still. So Brittany asks, what kind of force is it? Well, the kind of force that acts on a charge is an electric force. Or the electric force is the charge times the electric field. So Brittany agrees with Alec that there is an upward force. It's just Brittany says it's due to an electric field. So she says if my charge experiences an upwards force, it must be in an electric field which points up. So Brittany sees an electric field pointing up, and that's what produces on the force. So I think now we have to ask, who's right? So we have two different ways to describe that force. Which one is the right answer? So if we're asking who's right, Alec or Brittany, I would have to say that they are both right. They both have different descriptions of what's happening, but both descriptions are valid. So Brittany sees an electric force on the charge where the electric field points straight up. So there's the electric field as seen by Brittany. Alec sees a charge moving in a magnetic field that points into the page like this. So they both see a force, same size, same direction. They just describe it in different ways. Alec says that the force is QV times BA. The V in this equation I have written is C to A, so charge to Alec. That's the same as Brittany to Alec, because Brittany is running with the charge. So if those two forces are identical, it tells us that Q times EB, so the electric field seen by Brittany, is equal to Q, velocity of Brittany to Alec, crossed with the magnetic field as created by Alec. Can divide both sides with charge. We're left with the result, our conclusion, that the electric field as observed by Brittany is equal to the velocity crossed with the magnetic field as observed by Alec. It's almost like a magnetic field turns into an electric field when Brittany runs past Alec. So whether a field is an electric field or a magnetic field depends on your point of view.